Hey everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years. This is the show where I answer your burning questions about space and astronomy. You can ask your questions anywhere across my channel, on any YouTube comment, but also you can show up for the live show. We do this every Monday at 5 p.m. Pacific time. Now we're going to try a new experiment this week, which is that we want to try and have a bit of a game, bit of a feedback loop, a bit of a chance to give you some credit. And so we're going to have a little code that's going to show up with every single question that gets asked and answered. And so then in the comments, if you have a question to ask, also reference the code of the question that you thought was the best this episode, or just put in the code for the question that you thought was the best. Just put it in the comments, and then we will count up all of the votes essentially, and we'll give a shout out in the following episode, and or maybe use that as a chance to dig in. It'll tell us what you're most interested in. So please, when you see that little code down at the bottom, go ahead and add that to your question, a comment, the one that you thought was the best. All right, let's get into the questions. Scott Collins, are there any planets we've identified that are in a position where they could see us by the transit radial velocity? Yeah, absolutely. And in fact, astronomers know the exact number. There are 2,034 nearby star systems where aliens could detect the existence of the Earth thanks to the transit or radial velocity method. And so the way these work, right? The way we detect exoplanets is sort of two main methods. There's the radial velocity method, where you measure the light coming from a star as it's heading towards the Earth. And as the planet is orbiting around the star and the planet are kind of pulling on each other with their gravity, and the planet essentially is yanking the star back and forth, to and fro, away and towards us. And if they're lined up where the planet is essentially on the same plane as the star, then you can detect a change in the redshift of the light that is coming from that star. Essentially, the star is moving a little bit towards us, and the light blue shifts, and then the star is moving away from us a little bit, and the star red shifts a little bit, and you can detect that difference. And what's really cool about this is it's so precise that, you know, it's measured in meters per second, that you could walk the speed that some of these planets are pulling on the star, and yet we can detect it, which is incredible. And that tells us. But you need to have the star and the planet lined up. The transit method is where the planet is passing in front of the star, and it dims the light briefly as we watch the light from the star. And from there, we can detect the existence of the planet. And every time, if the light dims every 20 days, then we know that there's a planet going around the star with an orbital period of, say, 20 days. And astronomers use the two techniques hand in hand to get all the information. The transit method tells you the size of the planet. It tells you the orbital period of the planet. The radial velocity method tells you the mass of the planet by essentially how well it's able to yank its star back and forth. And between those two, you can understand the density of the planet. And so that'll tell you it's an Earth-sized world, or it's a gas giant, or something like that. And so astronomers have looked out for stars that are lined up with the sun and the Earth. And so there's like this band of stars that are across the sky. And there are about 2,000 nearby stars where aliens could be standing there and watching, and they could see the light of the Earth dim the sun as it passed in front, and they would know that we're here. So we're going to have to figure out a way to hide from all of those aliens. Mohammed Wael Al-Rifai. Hey Fraser, love everything you do. Can we assume that the heavier elements we find on Earth were all formed in stars within the Milky Way galaxy, or some were formed in other galaxies? I'm wondering if some of the iron in my blood was once in another galaxy. There's a really famous quote from Carl Sagan that we're all made of star stuff, that the iron in our blood, the calcium in our bones, the silica in our blood vessels, all the stuff comes from dying stars, from the universe around us. And I wouldn't say that it's coming from another galaxy, although, I mean, like, maybe in really powerful events, atoms could go a really long way from galaxy to galaxy, and maybe they could show up here. But they definitely came from other stars. So I want to talk a bit about just like some of the sources of some of the interesting things that are in your body. So you're made of mostly water, and that's made up of hydrogen and oxygen. The hydrogen is the primordial hydrogen that's left over from the Big Bang and was then used to form water and, of course, other substances that we have here. Heavier elements like helium, some was left over from the Big Bang, some was formed in stars and then blown off into space. Heavier elements like carbon, silicon, neon, things like that, those can be formed at the cores of more massive stars, and sometimes they'll release them when the stars die, but they can also just kind of puff them out in layers out into space, and they'll make their way through enriched clouds of star-forming material, and those can form planets. The heavier elements, like the iron that you mentioned, those come from supernovae. So when a star is, a really massive star, many times more massive than the sun, is going through fusion at its core, it runs through all the elements, the lighter elements, moves to heavier elements, and when it reaches iron, this is the equivalent of like ash. It can't extract any more fusion energy out of iron, and so the star just dies, collapses on itself, creates a black hole or a neutron star, and explodes, and a lot of that iron makes it off into space. And then the other thing, and this is a fairly recent discovery, is that neutron stars can collide with each other and turn into this thing called a kilonova. And we think that a lot of the heaviest elements, the gold, uranium, things like that, are formed when these neutron stars collide. And then there's also the regions around supermassive black holes, the accretion disks, act like the insides of stars. While material is being gobbled up by the black hole, it piles in so tightly that you get this essentially giant ring, accretion disk around the supermassive black hole that is like a star, and heavier elements are being formed inside that and can be thrown off into space as well. So yeah, when you think about just your body, everything around you, literally anything that isn't hydrogen has a very interesting story about how it got to form you. And I wouldn't say it came from another galaxy, but definitely came from other stars, generations of stars that lived before you, before us. And yet here we are. It's incredible. Gottenham. If we shot two perfect lasers parallel to each other, would they diverge or diffuse over a long enough distance due to the expansion of space? So this is sort of a fundamental question that astronomers have wanted to know. Like if you took two lasers here on Earth and you put them parallel to each other and you fired them off, the lasers would actually diverge away from each other until they reach the equator. Say you're on like the South Pole and you shot the lasers off. They would diverge until they reach the equator, and then they would converge back up to the North Pole. And from that essentially divergence and then convergence, you could actually measure the size of the Earth, the curvature of the Earth. And so when you fire those two lasers off into space, it's the same thing that happened. Will parallel lines remain parallel forever? And this was a big question in astronomy. And so astronomers went and looked for some of the largest objects that they could see in the universe. And these are giant features in the cosmic microwave background radiation, blobs of hot and cold that eventually will turn into the galaxy clusters that we see around us. And they looked for to make big triangles out of this and to measure the curvature. And from what they can tell, to the best that they can know, is that the lines don't diverge or converge. They would remain absolutely parallel. And this is why astronomers say that the universe is flat, that there is no curvature, overall curvature. The universe is not spherical. The universe is flat. And we've done a bunch of episodes on this. But to answer your question, if you shot two lasers in space, they would remain perfectly parallel forever. Now, practically speaking, yeah, the lasers would expand and diffuse over time, and then they would just become hard. You wouldn't be able to see them as lasers anymore. But if you had sort of like perfect imaginary lasers that could never separate and could never sort of expand in their size, they would just go on forever, perfectly parallel in the universe as we understand it today. Ricky DeRook. Hey Fraser, considering all your knowledge about the universe, do you think that the creation of all of it is a coincidence, or do you believe in some form of higher power or a creator? I have no idea. I don't know. I think the best answer to that question is I don't know. And there is insufficient evidence to make a decision either way. And I think that anyone who gives you an answer, it doesn't have sufficient evidence. So let's wait. Let's just explore the universe as we find it around us. Let's let nature tell us its secrets one at a time and search for whatever answers that we find interesting and look forward to being surprised by the results when we do. Phase shift. What are your thoughts on space debris and the number of satellites floating out there? I am a little nervous about the amount of material that's being launched into space. When I started doing this work, I think I did an article where we counted up the number of satellites, and there was like about 1,000 satellites. And now there are a couple of thousand satellites, and then also about 3,000 Starlink satellites. Not to mention OneWeb is going to be launching, and the Kuiper constellation, and the Chinese are going to be launching theirs, and the Russians are going to be launching theirs. Like, we are going to have a lot of satellites launching. But there's you need to really break down the risks of space debris into two parts. There's the low Earth orbiting space satellites, stuff that's orbiting like around the height of the International Space Station and below. So around 500 nautical miles, like under 1,000 kilometers is the stuff that's relatively close to the Earth. And that's really important because that stuff is in a more dense part of the atmosphere and is experiencing an atmospheric drag constantly. And so anything you launch in a fairly low orbit is just limited on how long it's going to stay in orbit around the Earth until it gets pulled back into the atmosphere and burns up. And so really any of the stuff that's launched low down is self-cleaning. It's the stuff that's higher is the stuff that you got to worry about. Stuff that's above 1,000 kilometers will last decades, hundreds of years, thousands of years. Stuff that is launched all the way up to geostationary orbit is effectively going to be there forever. And so there is a class of satellites that are launched in this kind of middle zone, which are a big worry because eventually if you launch a whole bunch there, if they collide with each other, they'll produce a bunch of debris. The debris will hit other satellites and you'll have this cloud that surrounds the Earth and it's not going to be coming back into the Earth's atmosphere. And so I think this shift to lower Earth orbiting satellites like Starlink, like Kuiper, etc., is actually a good direction to go. Space is enormous. Even the area around the Earth is gigantic. And if we if we come up with some situation where two satellites crash into each other, the debris is going to clean itself up in a very short period of time. Like if a Starlink's Krypton engine goes offline, it's dead and reorbits within a few months, a year at the maximum. So I would actually like to see more satellites launched into low Earth orbit than fewer satellites launched into these higher, more permanent orbits. I think that's like a long-term space junk problem that we need to deal with. So I'm not that worried. Space is big, but I do think that is something that we should be concerned about. And I think you need to have a really good reason if you're going to be launching your satellite into one of those permanent orbits, and you've got to have a mechanism for bringing that satellite back down when you do. Rabindra Mishra, what's your take on ISRO? ISRO is the Indian Space Research Organization. I think I got the acronym right. And they're great. They've done a lot of really incredible missions. So the big one that you might be familiar with is Chandrayaan. There was the Chandrayaan-1 and then there's the Chandrayaan-2. And Chandrayaan-1 was the satellite that made the discovery of water on the moon. Now, there was a NASA instrument that assisted with that discovery, but essentially we didn't know that there was water on the moon until the Chandrayaan spacecraft launched thanks to India. Since then, India has launched the MOM mission, the Mars Orbiter mission, which has been incredibly successful. It's taken some wonderful pictures of Mars and was done on shoestring. Now we saw the Chandrayaan-2 spacecraft that has gone to the moon. They had a lander. The lander didn't work, but the orbiter is still there. And we're going to see a lot more missions like this from India. And I think it's great. Like just to have all these different countries. You've got a mission from the United Arab Emirates at Mars. You've got the Chinese with rovers and landers on Mars. You've got the Russians with the work that they've done in the past. I know things are a little weird right now, but hopefully they will come back around. And then, of course, you've got NASA, the European Space Agency. So the Japanese are amazing. The Koreans have gotten into the game now. There's the Australians are building their own launch facility. We're probably going to get a launch facility here in Canada. And I think that's just good. Like, I think that having more countries involved in space exploration, either with their own missions or collaborations, is the way to go. Like, knowledge should be for the benefit of all humanity, and to see these different countries getting to the point of technological development where they're building space missions is really exciting. So more, please. Wrong time, Weeder. Do you think the universal speed limit will ever be broken? I have no idea. Probably not. Like, if I had to follow my gut, will we ever go faster than the speed of light? My gut says no. That if we could go faster than the speed of light, then alien civilizations could go faster than the speed of light, and then it makes the Fermi paradox even weirder, because we don't see any aliens in the sky, and we would think that they would be traveling as maximum to the speed of light as would be possible, and yet we don't see them. But if they could travel faster than the speed of light, then they would be everywhere. No matter how far away they were, billions of light years away, they would be here. It's sort of like the same thing of do you think time travel will ever be discovered? Where are all the time travelers? Like, the world should be filled with time travelers, because you've got potentially an infinite amount of time in the future. And all these time travelers will be building their time travel devices, coming back now, or piling up into Hitler's bathroom. So that's why, just purely sort of from a rational thinking, I don't think that we'll ever be able to go faster than the speed of light, which sucks. Obviously, Star Trek has told us lies, but it might just be that we have to work with the universe that we find ourselves in. Peter Gerdes. How convincing do you find Hansen's great filter arguments? I find them very interesting, but I'm not that convinced. Too easy to abuse anthropic reasoning. So if you missed it, I had an interview with Dr. Robin Hansen, who is the developer of the idea of the great filter, this idea that there must be some catastrophic event that could be waiting for us, that stops all intelligent civilizations from advancing. And he proposed a bunch of ideas. And yeah, I mean, I pushed back a bit in the interview, and you should definitely listen to it. But my general feeling is that, if we can anticipate the great filter, it's not the great filter. Because the great filter takes out everybody. And so if you can say, well, okay, so maybe it's the robot uprising. Well, let's not build robots. And it all takes is one civilization to not build the robot uprising, and then they explore the entire universe. And so nobody has thought of the answer to this problem. In terms of alien civilizations, no alien civilization has thought this through, has been able to prevent it. And so my feeling about the great filter is that not only will we not anticipate it, we cannot anticipate it. It is impossible to anticipate, and it's impossible to avoid. That's my feeling. More questions in a second, but first I'd like to thank our patrons: John J. Gasparovic, Dwayne Duval, Tyler, Robert Giacinto, Timothy Ponder, and the rest of our 839 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. Production effect. If we encountered life, no matter how well developed, what is the plan to engage or avoid contact, especially knowing contact could contaminate the life form? This is this idea of planetary protection, and there's a whole group at NASA that's trying to work through this problem, both how do we prevent species here on Earth from infecting the life on Mars, the biomes on Mars, potentially killing off local life forms or eating it, or whatever, and then vice versa. How do we stop any weird aliens, any bacterial samples, anything that we find over on Mars from replicating here on Earth and wiping us all out from some infection? Both of those possibilities are fairly extreme, because Earth life evolved to live on Earth, and Mars life evolved to live on Mars, if it exists. And European space whales really only enjoy the depths of the European oceans. Be hard for them to live in the Earth's oceans, but it's a risk. We've seen time and time again that invasive species here on Earth have a tendency to take over, to outcompete the local creatures. And if we can prevent it, we can learn from our lessons of invasive species here on Earth. Let's do it now while there's still time. So essentially, if you've got a rover that's going to be going to a region of Mars that you think could have life there today, you've got to take the rover apart bit by bit. You got to bake each piece of the rover in an autoclave. You got to get really hot, kill off any bacteria in it, and then put it back together very carefully in a clean room with people wearing bunny suits so that there's no way that they could be transferring their filthy Earth bacteria onto the rover, and then you package it up and you send it to Mars, and it's still got a little bit of life on it. Like, just Earth life is so pervasive. And then when we bring life back from Mars, you're going to probably have to take it to some secure facility, a place where you can open it up in an environment where if there is any life forms inside, you're not going to contaminate immediately with life from Earth, but also that any life that's inside of it has no way to escape this facility and run rampant here on Earth. So as we are getting better and better at exploring other worlds, scientists are putting more and more regulations in place to minimize the chances that we're going to be risking this planet-to-planet species transfer. Stacks. Do you think Pluto has an atmosphere when orbiting closer to the sun, then freezes out farther away? Yeah, this appears to be what Pluto has. So astronomers first figured out that Pluto probably has a tenuous atmosphere by doing occultations. So they watched when Pluto passed directly in front of some distant star. And as it did, they were able to measure how the star dimmed a little bit and then got blocked by Pluto, and then dimmed a little bit and then was fully illuminated again. And they were able to essentially measure the existence of the atmosphere on Pluto. And we got much better images of the atmosphere on Pluto when NASA's New Horizons spacecraft did its flyby. And the coolest pictures is when New Horizons was leaving Pluto and it looked back, and Pluto was backlit in the sun, and you can see this incredible blue atmosphere above the surface of Pluto. And the thought is that when Pluto gets to the closest point of its orbit, which it sort of is right now, it warms it up enough to the point that its atmosphere sublimates and puffs up. And then as it moves farther and farther away from the sun, it cools down, it gets colder and colder, and this atmosphere freezes out, snows down on the surface, piles up in drifts, and spends most of its time as snow on the surface of Pluto. And then as it gets closer, it warms up, puffs out, and so on. And it's incredible that we have pictures of this. Series K. Lee, we leave bags of poo on the moon. How long until we leave bags of poo on Mars? I'm going to guess the first bag of poo thrown on the surface of Mars will be 2035. That's my guess. D suits. Where you live now, do you regularly find Starlink traces in your telescope images? You once said you had good service, so can you see that service? So can I see the Starlinks that are providing me internet? I haven't tried yet. So because I'm living out of a trailer right now, it's sort of a rough existence to get the telescope out. So I haven't been doing any astrophotography, but I have great plans to do so. But I talked to a lot of the other astrophotographers, and people are definitely seeing Starlinks in their images. But you typically only see the Starlinks when they're low to the horizon. So you usually see them shortly after the sun goes down or before the sun comes up, within a fairly narrow band, 20, 30 degrees above the horizon. And that's a bad place to do astrophotography. You tend to avoid that. You try to look directly overhead, and at that point, the Starlinks and other satellites are already in the shadow. Now, in the summertime here in the Northern Hemisphere, as far north as I am in Canada, then you can actually see satellites throughout the entire pass. Like, I can see the International Space Station fly completely overhead in the summertime, sometimes twice or even 3 times, one pass after the other, and it's illuminated almost the entire time. But it's the astronomers, it's the professional astronomers, the ones who they have to image whatever object they're looking for the moment it comes up over the horizon as long as they can. They only get as much telescope time, and so they'll image even when it's sort of down, lower to the horizon, in the murk of the atmosphere if they have to get that data. And a lot of the times they're the ones that are starting to get these trails coming through their images. Visually, you can't see them. I mean, you can't see Starlinks. They're just not bright enough. You can see them when they've first been launched and they make this kind of trail as they're moving along the sky and they're moving up into their final operational altitude. But then after that, you can't see them. So even though there are thousands and thousands of them up there, you can't see them with your eyes, even with really perfectly dark skies. 1992 UFO. Is there a limit to how big a single object can get in our universe? So when you think about, like, what is an object? Like, the Earth is an object. The sun is an object. The Milky Way is an object. It's bound by gravity into a single cohesive thing. And as the universe continues to expand, the gravity of the Milky Way is going to hold itself together. The local group, the combination of Milky Way, Andromeda, M33, some of the other dwarf galaxies around us, they're held in mutual gravity. They're an object. Beyond that, the expansion of the universe is carrying stuff away from each other. So we're part of a larger collection of galaxies called the Virgo supercluster, but the expansion of the universe is going to tear the Virgo supercluster apart. And you've probably heard there's like the Laniakea supercluster and bigger objects as well, and they're going to get even more torn apart in the far future. So I would say the largest object that isn't going to be torn apart by the expansion of the universe is the local group of galaxies. Milky Way, M33, Andromeda, a few dozen dwarf galaxies that will eventually coalesce into one giant mega galaxy in the far, far future. That's the biggest object. Nick Poshek, do you think there is potential for space science startups? I'd love to see a SpaceX for science missions. It's really tricky because the way science is funded in this world, you've got pharmaceutical companies, things like that, that are doing science. They hire scientists, chemists, things like that, but they're trying to make a profit from it. But a lot of like basic science, space-related science, there's no real short-term profit that can be made from it. And so that's the role of governments. Governments are there to provide funding for activities where there's no defined outcome beyond the knowledge that we can gain. And so you would need a group of individuals who are working together that are spending money to do science, but they will never experience a profit. And that's really tricky to convince people to do. And, they call that charity. And so, there are nonprofit organizations that participate and contribute to space exploration and space science, but it's a big ask. And so that's why it generally falls under the purview of governments. Timberwolf, what are your views on a colony on Mars? Surely the low gravity would affect those living there over time. Yeah, I mean, I've mentioned many times that I'm not a huge fan of the idea of a colony on Mars, just because I think that Mars sucks. It's the worst. There's no atmosphere. There's no plants. There's no oceans. There's just vacuum, radiation, and rock and low gravity. And I'm sure it's adventurous for a lot of people and they want to go live on Mars. That's cool. Like, I'm not going to stop you. Do it. I can't wait for you to send me your vlogs of the life that you're living on Mars. It's just not for me, and I don't think it's for a lot of people. But all of these issues, the radiation, you can live underground. The water, you can extract water from ice. And air, you can create air out of the water. There's lots of local resources that you can use on Mars to survive. But the one that's really tricky is the low gravity, because there's just no way to make more gravity. Unless, again, this is not Star Trek. We have no way to artificially increase the amount of gravity that your body is going to experience. And we don't know what 1/3 gravity does to the human body. We don't know if babies can gestate properly during pregnancy, if there's going to be birth defects, if children raised under 1/3 gravity are going to develop properly. We don't know the answer to these questions. More research is necessary. And to send people to Mars, to give people the opportunity to go to Mars and for them to do what humans do and make babies, is a very dangerous science experiment before we've gathered a lot of information. And the only way we can gather information is to do research in simulated low gravity environments, like a rotating space station in orbit around the Earth, to have mammals try to give birth and gestate, and then have larger mammals and eventually monkeys, and go through a fairly long lifetime to make sure that that there are no problems with creatures living their lives on Mars. And if that works, then fine. Then the gravity problem is not an issue. There are a few ways around it. There's an idea of a gravity train where people could go and spend a good chunk of their day on this sort of like a Ferris wheel that's turned on its side that's giving them some amount of gravity to fill in for the missing gravity. So that sounds fun. So surprisingly, space itself, orbital colonies make more sense because you can spin up the space station to give full artificial gravity. Just as if you were standing on Earth. You can have shielding that'll protect you from cosmic radiation. You can have solar panels that are gathering energy. You can have harvest resources from asteroids, comets, things like that. So yeah, I mean, until we sort out the low gravity problem, we don't know. It's a bad idea to try to live on Mars. And nobody has plans to solve this problem. Nobody has plans to perform these experiments yet. And so if people just go live on Mars, they're going to perform these experiments in real time, possibly with disastrous results. Moonwalker. If astronauts are falling around the Earth, how come they don't feel any centripetal force? Astronauts are in perfect balance. They are, because of the speed that they're going around the Earth, they're going 28,000 kilometers per hour. They are essentially attempting to fly off into space. And then at the same time, the gravity of the Earth is pulling them down. And those two forces, the force outward, because you're traveling at 28,000 kilometers per hour, perfectly balances the gravitational force pulling you inward. And so if you have two forces acting on you perfectly equal, then you experience no change in acceleration. You experience no gravity. And so as long as all those forces are in perfect balance. And you're experiencing perfect balance force right now. You're sitting in a chair. The chair is pushing up at you. You're pushing down on the chair against the force of gravity. You're in perfect balance. When you think about this, when you take this in your physics class, you figure out all of the balance of forces that are affecting you at all times. But yeah, that's why they feel like they're in zero gravity. Dukeg 1848. Hey Fraser, really appreciate the channel. My question is space always a vacuum? What is space vacuum anyway? Well, space isn't exactly a vacuum, but we have this very Earth-centric view of what is normal. Like you are at the bottom of a gigantic ocean of air that is hundreds of kilometers thick, that is pushing down on you with incredible force. And that is because the Earth's gravity is holding on to this atmosphere. This atmosphere would love to just fly off into space and just be individual particles just zipping between the stars. But the Earth's gravity is holding this atmosphere around us and holding it so thick that you can breathe, so thick that your skin doesn't bruise. But without the Earth's gravity, the atmosphere would just disappear right away. And so if you go out into space where there isn't gravity close by with that kind of force, then you've got what the atoms really want to do, is just fly and be free through the universe. And still, if you go and grabbed a cubic meter of space and examined it, you would find a handful of atoms just floating free in space. There's going to be more in a place like the solar system. There's going to be less in interstellar space, and there's going to be even less in intergalactic space. And so really, a place like the Earth with an atmosphere is not normal, right? It's only when you have the gravity to hold it down that you'll actually get this kind of concentration of atmosphere. So there is no place that is a pure vacuum. You will always find particles, even in the pure depths of space, just not very many. Mokenchi, how soon do you think asteroid mining is? Well, I think asteroid mining has already happened. When you think about the Hayabusa 2 spacecraft, even the Hayabusa 1 spacecraft, they grabbed a tiny little sample of the asteroid and they brought it back to Earth. Asteroid mined twice. And then, of course, you've got the OSIRIS-REx mission at Bennu. It grabbed a sample. So now 3 asteroids have been mined. But that's not what you're talking about, right? Like, how long until we send out robots that are dismantling giant asteroids and mining pure gold and bringing that gold back to Earth so that we can all be rich and live in gold houses because there's too much gold? And the answer is probably never, I think. Earth is the biggest accumulation of of elements in the solar system, the heavy elements that's accessible in the solar system. And obviously, there's more iron and stuff in Jupiter, but it's, it's down in the middle of Jupiter, and there's more in the sun, but it's in the middle of the sun. But Earth is a giant rock ball, and there's rock and metal ball. There's lots of that material that you would want. And it's really easy. You just got to dig in the ground and you can grab it. So it really does not make financial sense to go out into space with all the expense, to go to some other object, to chase it down, to set up robot factories on that and try to mine it. What harvesting resources from space, where that makes sense, is when you need to use them locally. So if you're going to build some kind of robot factory on the moon, you're going to want to harvest your resources from the moon. If you're going to want to set up a supply depot at an asteroid, you're going to want to set up your propellant factory on that asteroid. But I don't think that we will ever, never is a long time, but I don't think we will ever have a time when we are harvesting resources from the asteroids and sending them back home to Earth for us to use. It just doesn't make financial sense. There's too much of all that stuff just under our feet all the time. Indra, how do supermassive black holes form? We don't really know. A supermassive black hole is one at the heart of the Milky Way, 4.1 million times the mass of the sun. There's one at the heart of Andromeda, like 100 million times the mass of the sun. That's a very massive object. And the farther that astronomers look out into space, the further back in time, just to hundreds of millions of years, they are detecting supermassive black holes. And so the one idea originally was that supermassive black holes formed through the mergers of smaller. You had giant stars, the stars died, formed black holes, the black holes merged, a bunch of them merged. You had 10 black holes that emerged over here, formed 10 over there, they merge, you get 20 mass black hole, and so on and so forth. But it seems like they're too soon, that the supermassive black holes were already fully formed just too early into the universe. And so the other theory is that they just formed directly, that you had this giant ball of gas and dust that just collapsed down in on itself and turned into a giant black hole directly without having to go through all those intermediate steps. And then the third possibility, and not a lot of people believe this, is that they could be primordial black holes. So back at the beginning of the universe, there were overdensities and underdensities, and it's possible that those regions that were overdense just turned into black holes right at the beginning of the universe. And so we should have these, of all sizes, supermassive black holes with less mass, black holes down to the mass of an asteroid or a house, could have been all existed at different masses. And then the supermassive black holes that started out just gathered more mass and sunk into the bottom of galaxies and galaxy clusters. So, but right now we don't know. It's one of the mysteries in astronomy, which is like, how do they get so big so fast? Let's find out. All right, those were the questions from this week. Thank you, everyone who answered the questions either anywhere across my YouTube channel or joined for the live show, which we do every Monday at 5 p.m. Pacific time. And don't forget, we ran little codes at the bottom of every question that we did. So go ahead, and if you have a question or you just want to make a comment, or just post the code for the questions that you thought, or the question that you thought was the best, and we will count them up and we'll give a shout out to the questioner on an upcoming episode. All right. Thanks, everyone. And we'll see you next week. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.